All right, this is your stat sensei, and this will be the last video on one sample T hypothesis test. This is a good one to watch because we're going to actually work with data as opposed to summary statistics. So here we go. A steel supplier claims that their bars have an elongation of 40%. So this is the claim, this is the belief that it's 40% under a stress of 10 metric tons. Kind of superfluous information. A random sample. So we have a random sample. That's going to be nice for the condition. That means this is my sample size of steel bars was taken from a warehouse and the elongation was measured in percent. Here's where our observed values. So this is our list of data. All right. And if I counted them up, we have 12 measurements. So this would be 39%, 41, etc. Is there evidence at a significance level of 0.05? Oh, so they're telling me they want me to test this at alpha equal 0.05 to demonstrate the elongation was different from 40. Different is a key word, and different tells me I'm working with a not equal situation. All right, so a null hypothesis is mu is 40% because that's what the general claim has been. What we're looking to find out is it different? Which means, could it be more than 40% or could it be less than 40%? So technically what we want to know is if this is at 40, we want to know if it's too far up here or if it's too far this way. All right. Obviously it's going to be one or the other. It can't be both, or it may be neither. It may be neither, or it can be one or the other. So let mu equal the true population mean for the percent of steel bar long elongation. All right. So that's our defining our parameter. Condition, random sample, it was given. Why? They told us a random sample right there. How many bars were in our sample? 12. So this is going to be 12 times 10, or I like to do the divided by 0.1 equals 120. It's reasonable to assume that there are at least 120 steel bars. I'm sure they produce a ton of steel bars. So I'm sure that they make more than 120. And even if they didn't, we're going to assume that they do. Now, the next thing is, it doesn't say that the underlying population is normal. And our sample size is less than 30. If our sample size is less than 30 and they don't tell us anything about the population, I'm going to need to enter that data into stat edit. So I go to stat edit and I've entered all my data. There's 39, 41, et cetera, et cetera. And I need to check to see whether or not I have a normal box plot or normal enough. So I'm going to go to y equals, and I'm going to clear out all this junk because all this junk will mess up me doing my graph. So go to y equals and turn all that stuff off. All right, and you need to scroll all the way to the bottom. Then I'm going to quit, second quit. And I'm going to go to second stat plot, and I'm going to turn. I want this one, the first one on, but all the rest need to be off. So I'm going to drop down and turn this one off. Right? Now it's like, okay, on, and then 2 and 3 are off. That looks good. So now I'm ready to draw my box plot. So press enter down at the bottom. Arrow over, so this says on. And then I'm going to drop down and scroll to the right until I get to the box plot that shows outliers. Because if I have outliers, I have a problem. I'm going to drop down my data list. I saved it in L1, so press second one, because that's where it's at. And I don't worry about the mark at all. And I should be able to press zoom 9. Now, every now and then your calculator will do something like this. I don't know why. So don't stress. Press clear, and then press zoom 9. And there's my box plot. So I usually sketch it out just the way it is. And then I label the major values, or tend to. And here's the way you get your major values. You can use the trace feature, which is right here, this button. And we find the minimum was 33, Q1 35, 38, 40.5, and 42. All right. And you can either label these or you can draw a scale and make sure you label it. All right. Well, while I look at it, The box plot is reasonably symmetric with no outliers. The distribution appears to be approximately normal. Once again, very important that we say approximately normal. All right, so I write down my formula. T equals x bar minus mu s divided by the square root of n. We're going to ignore the 2 for just a moment. So what we got here is, well, actually, you know what? Let's go ahead and run this thing, and I'll show you what's happening. We're going to go stat or all the way over to test, t-test. Make sure data is highlighted. The claim mean was a 40%. That's what we have up here. All my data is in L1, so second one. And my alternative was that it was not equal to 40. And I press calculate. And I got all these values. Well, initially, our initial claim was that it was 40. Our sample, our X bar, said, no, it's not 40, it's 37.58. All right. So we're actually interested in that area, 37.58. That's the area we're interested in. And we also have our sample standard deviation of 3.17. So there's my X bar, 37.58, minus my claim of 40, divided by my sample standard deviation that came from the data, divided by 12. All right. So that's where that came from. But notice I had to put a 2 times in front. I only do this for the 2-tailed test. I only do this for not equal. So if it's a not equal, put the 2 times in front. All right. And we ended up with, remember the t, this is our actual values. The t says this is a 0 mean, and we ended up with a negative 2.6, negative 2.636. All right, so just as extreme as negative 2.636 would be a positive 2.636. And so the doubling means it could have been either way. All right, we have to have that 2 there. Then we need to write down our t statistic, must have this value. And our p-value is 0.0231. In this case, they told us to test at an alpha level of 0.05, significance level of 0.05, and 0.0231 is less than 0.01, 0.05, all right? And remember, make these the same length. 231 is less than 500. And if I look at my recipe, if the p-value is less, we reject. So our p-value is 0.0231. We reject a null. There is sufficient evidence at alpha equal 0.05. And this just came from our calculation. This was our decision. There is sufficient evidence at our test level to suggest that the true population mean for the percent of steel bar elongation, that was our definition above, is different, or if you wanted to, is not equal to 40%. And once again, that's a restatement in words of this. So is different than 40% or is not equal to 40%. All right. Hope that helps. And I hope you see how it matches the conclusion format. Thanks for watching. I hope this is a beneficial